Okay, next we will see the instruction formats. So the control unit within the CPU interpret each instruction code and provide necessary control function which is needed to process the instruction. Means it generates the control word for that. Okay, so common fields found in the instruction formats are operation code, right? Then the address and the mode. So the instruction like add a comma b, so add is your operation code, then a or b it can be memory address, your registers, and the mode field which specifies the way the operand or the effective address is determined, whether from that address I need to take directly that value, or it will specify me the another address from where I will get the operand. So number of address fields in the instruction format of a computer, it depends on the internal organization, and with your that computer, the structure, instruction structure that is given, right? And basically there are three types of CPU organization based on this instruction formats. So they are single accumulator organization in which accumulator register is used, then general register organization in which the use of registers which is available in CPU that is used, and your stack organization in which the stack is used. Okay, so let's first see the first CPU organization, that is single accumulator organization. So in this all operations are performed within an implied accumulator registers, right? So they will use the accumulator register only. The instruction format in this type of computer uses one address field, right? So for any operation you require two operands. So one operand, they assume that one operand is already there in accumulator, otherwise you need to bring in accumulator, and for other you need to specify the address. So only one address we need to specify. Suppose add x, right? Add x. This is the instruction for single accumulator organization. You can see this is the operation, and here this is the address, and we are specifying only one address. So what this instruction does, it will perform this operation. So add x means this is giving address. From that memory location, it will get the value, add with accumulator. Whatever the value you have in accumulator, it will add with that and store into accumulator only. So this thing can be written using this instruction, right? So your single accumulator organization in such your instruction is like this. Okay. Here your AC, that is accumulator register. Your MX, it symbolizes the memory word located at address X, means your operand. And this is one address type instruction because there is only one address in your instruction. So this is one address type instruction. Mhm. The second is general register organization. So in general register organization, the instruction format in this type of computer uses three or two address field. In previous case, there is only one address field, like add x, only one address. Here, three or two address fields. So add R1, R2, R3. So if I want to perform this operation R1, R2, R3, so two register R2 plus R3, add it and store the value in R1. So in this case, I need to specify the instruction like this: add R1 means destination register, comma R2 first operand, comma R3 third operand, second operand. So this is the general register organization. You can see the length. This length is smaller. This is the large length. Okay. So this is three address R1, R2, R3. Then 2 add R1, R2 to denote R2 plus R1 plus R2, and result will be stored into R1. So the first register will serve as a operand and your destination register. So operation will be performed like this: R1 plus R2, and then result will be stored into R1. So you can see two address. This is two address. So your one of the operand is your destination register as well. Then you can use this to address instruction. Each address field may specify a processor register or a memory word. So right now you are using processor registers only. This can be a memory location as well, as we have seen in the previous case. So it can be add R1 comma X. In that case, this is R1 and R1 plus M of X. Right. So this is memory word. So 3 and 2 address type instruction that belongs to general register organization. Then next is stack organization. So in this we have a push and pop instruction which require an address field. Push and pop instruction, right? In previous case we don't have such push and pop. Now here push and pop instruction will require the address field. So push X means from address X, right? From memory it will get the word, and on top of the stack it will push that value, right? It will push that value. Operation type instruction, it do not need an address field, means your add, just you need to specify add, that's it. It don't require any address field. Why? Because when you specify add, what it will do, from top of the stack it will pop two values or two operands, add it and then again push on the stack, right? Again it will push on the stack. Add will pop two numbers from the stack, add them and push the sum into stack. So using push X, what it does, it will push the value into stack. So suppose push X, so it will from memory location X it will push the value, and next push Y, so memory location Y it will push the value. Now then I will specify add. So what it will do, it will take out this value, it will take out this value, add it, and then result will be stored in this. So after adding, the result will be the addition of X and Y, means whatever value you have in at that address. Okay, so this is called a zero address type instruction. This is called address type instruction. So in stack organization, in such CPU organization, we have seen this is a zero type. In register organization, general register organization, we have two or three address. So we have 0, then we have 1, we have 2, and 3 address type instruction. So this 0, this belongs to stack. If your organization is stack organization, then we have 0 type as instruction. Our instruction that we are specifying is a 0 type instruction. When you have a single accumulator organization, right? Accumulator organization, at that time you have one address type instruction, right? So what we are doing in this case, push and then add. In accumulator, add X. So 2 and 3, so general register organization, General register organization have two or three. So if I write add R1 R2 or add R1 R2 R3. So addition of R2 R3 will be stored in R1 or R1 R2 will be stored in R1. Okay, so this is the stack organization. Now let's see the example. We'll take one operation, and then for all address type instruction means in our instruction the number of address fields can be 0, 1, 2, and 3 based on the CPU organization, right? So let's evaluate the arithmetic statement x is equal to a plus b star c plus d using this 0, 1, 2, and 3 address instruction. Okay, so the operation that are required is addition for this, then uh, sub, right? Like you can use this sub, but right now we don't require this sub. Then multiplication for this, right? So if you have some subtraction operation that can be used here. Okay. Then move, it's a transfer type operation. Then your load and store for transfer to and from memory and accumulator register. Operands are in memory address A, B, C, and D. Right? Wherever operands are there, right? So operands are at address A. Wherever the address A in main memory, there at that location we have a operand. Right? So that value we need to fetch from memory for A, B, and C and D. So these are the address. And result must be stored in X. So ultimate result, this addition that we need to store or add in X. Okay. Load and store to transfer and to get the memory in accumulator register. Now let's first see the three address instruction. Okay, which is more popular. So X, this we want to perform A plus B star C plus D. What you need to do? This is a three address instruction. So you can use three instruction. You can use three address. So what we can do? Get this value using memory. Get this value. Okay. Then store the result somewhere. Then second, get this value. Get this value and store it somewhere. And then perform multiplication on this, or take intermediate R1, R2, and multiply R1, R2, right? And store the result in X. Let's see this. So add R1 comma A comma B. So what this instruction will do? It will perform this. Take the value from memory address A plus memory address B and then add it and store the result in R1. This instruction. This is called instruction. This is called instruction. And to perform this instruction, we need to specify control word that we have seen previously. Okay, now next, add R2 comma C comma D. So for this, same thing. Then what? We have intermediate result R1 R2. Now multiply. So multiply R1 R2 and we want to store the result in X. X means at memory address X, we want to store the result of this. So after multiplying R1 R2, the result will be stored in X. For that, you need to write this instruction. So this instruction will do that. So for this, this is your assembly code. If three address instruction is supported. So what is the advantage of this? Advantage of this format is it result in short programs. So only three lines. And disadvantage is The binary coded instruction require too many bits to specify three address. Means for this three address, right? This address must be converted into binary, right? So for that, the length of instruction will be large. It will be large. Okay. Then next is to address instruction. Next is to address instruction. So here for with your add and all, we can specify only two address, not more than two address. Okay. In previous case, yes, in we have directly given R1 A comma B. So whatever result you have A in B, that is transferred to R1. But now in two address, you cannot do this because this address you cannot specify. So what we will do for this, first we will transfer this value to some register, right? For this again we will transfer to some register, okay? Or if you don't want, then it's also fine, right? You can directly use with this because now your value is unknown. Okay, so let me write first instruction, move r1 comma a. So what it does, it will move the value from memory address a to r1, right? So move r1 comma a. So this operation will be performed. Now next, so now the content of a is in r1. Now with add you can specify only two address, right? So what you need to do, write like this, r1 comma b, only two address, and your a is in a and b is here, so that you can write add r1 comma b. So it will perform addition between r1 and address at memory location b, and the result will be stored in r1. So now this result in r1. In previous case, in previous case for this we have just written like this, add r1 comma a comma b. Now for this operation, for three address it can be written like this, for two address you can see two instructions instead of one. Now next, again same thing what we have done here, same two step you need to follow. Take this value into r2, add with d, right? R2 comma d and add. So that thing I have written here. So result will be stored in R2. Then multiply it, multiply R1 comma R2, and the result will be stored in R1. This multiplication result will be stored in R1. But what is our ultimate goal? We don't want result in R1, but our result must be stored in this address. So again you need to move from your register to memory location. So we have moved to that. Now see how many instructions, 1 2 3 4 5 6. So if you have two address type instruction, number of instruction are now 6. In previous case it was 3. Okay, so the first symbol listed in an instruction is assumed to be both source and the destination. Source and the destination if you perform the operation. Right? So this is source and destination also. Source, destination, right? And in previous case, the first is source, destination. These are the source. This is a two address instruction. Okay. Then one address instruction. So same thing we need to do with the one address instruction. Okay. So in this one address instruction, as we have seen the in accumulator organization, right? So accumulator will be involved here. So what you need to do? First, you need to get this value into accumulator. Then perform add operation with B. So when you write that, it will perform addition with your accumulator. Okay. So let me write for this. First, get load A means from this address, from the memory, the value will be loaded in accumulator when you write load. Okay. Then what next? Write the instruction, that is addition. Add B means it will perform addition operation with your accumulator. So what it does AC plus M of B. And the result will be stored in accumulator again. You need not to specify this, right? So what you are specifying? We are specifying the second source, right? From B you need to get the second operand. First operand is in accumulator and the destination is also accumulator. So you can see here we just need to write add B. In previous case we were specifying two address. Here only one address, right? Then after doing this, store T, because for this also I will use accumulator. So if I use accumulator again, this value will be overwritten. So I need to store in some temporary value. So this first I store this in accumulator, perform the addition with B, and store it into AC. Now this value I need to store in some temporary variable so I can use AC again. Right? So that's why store T, what it does, whatever the value you have in accumulator will be stored at address T in memory. So that value will be stored here in some temporary location. Now load C. So whatever we follow the step here, the same thing that will be done here. So AC, then addition with D. So add D. So it will perform the addition operation. Then what you need to do? This value is in AC. So now this result, this summation is in AC. This is in AC. This summation where it is? It is at this memory location. At this memory location. So so for that, what you can write? You can write mul t. So what it does? It will perform multiplication operation with your accumulator and one address or second operand you are specifying. First operand is accumulator. Second we have specified here, and then that multiplication result will be stored in accumulator, right? So result that is stored in accumulator. Okay. After that, we want to store this result into X. So we need to write store X. So in that case, the result of accumulator will be stored in memory location X. Right? So here you can see 1, 2, 3, 4, 5, 6, 7. 7 instructions are there. 7 instructions are there. The instruction length is now smaller, but number of instructions are more now. Okay. So here T is your address of temporary memory location, and all operations are done between the accumulator register and your memory operand. Now next is zero address instruction. So this zero address instruction, it does not use address field for the instruction add and multiplication. But yes, the push and pop instruction need an address field to specify the operand that are communicated with the stack. Okay. And to evaluate the expression, what is the expression? The expression was A plus B multiply C plus D. This was the expression. And to evaluate this expression must be in reverse Polish notation. Right? So if I convert in reverse Polish notation, then this will be AB plus CD plus star. This thing you have studied in your data structure. So AB plus CD plus star. This is the reverse Polish notation. Now your CPU will use this and then write the instruction. So what you need to do? First, it will push A, right? So at that time you require the address of A. So push A, right? So TOS, that is the top of the stack. Now it points to this. Then push B on the stack. So push B. Now top of the stack point to B. It will point to B. Right. Let me draw the stack here. So first push A, not this one because TOS is here initially, then incremented and it will be here TOS. Add it A. Then push B. So B and TOS top of the stack will be here. Then what? Then add. So add, it just need to specify add. So what it does, it will take out these two value B and A. B and A, add it and store the result and store the result here, right? Take out those two and store the result. So this will be discarded and the result will be stored, and this is your TOS now, right? Two value you have take out, add it and add it. Then push C, right? So now right now your content is um, this result I am indicating as let's small a1 and this is small b1, whatever you result have. So now it's a1 b plus a. Then it will push C, it will push D, right? D, then again plus means add, right? So it will take out this, pop this two value D and C, add it, and again it will store. So now your stack is like this, A1 and the result of C plus D, that is B1. After that, what you have? You have multiplication. So this two thing will be take out, perform the multiplication operation, and then that value will be pushed multiplication and that value will be pushed to your stack, right? So let me give that result as a C1, right? This is the result. So here this is the top of the stack, and here after this mul, this is the top of the stack. Now what we want? We want this result in X. So top of the stack you need to put at memory location X. So when you perform this pop X, the result from top of the stack will be moved to memory location X. Memory location. Okay. So this is zero address instruction. Okay. Now last is RISC instruction. Okay. So in this instruction set, the RISC processor is restricted to use of load and store instruction when it communicates between memory and CPU. We have seen in the terms of accumulator that to get store the value in accumulator we are using load, and to get the value from accumulator means for accumulator to memory we were using store. Now here RISC instruction set, it uses load instruction. So all the values will be first loaded from memory location to processor, and then the value, the operation will be performed in the registers with the help of registers, and then result again will be stored from register to memory location. So let's see the same operation again. So all instructions are executed within the registers of the CPU without referring to memory. In previous case, we were using the memory. So in this, first all the data that you require that will be brought to registers, and then operation will be performed. So A plus B star C plus D. So first bring this A, B, C, D, this address from memory to registers. So R1, load R1 comma A. So from memory location A, the data will be in R1, then R2, R3 and R4. So now we have this data into register R1, R2, R3. Now perform the operation. First is R1 comma R1 comma R2. This will perform this operation. Then add R3 comma add R3 comma R3 comma 4. So R3 plus R4 and result will be stored in R3. First result is in R1, second is R2, R3. Just perform the multiplication operation, that is R1 comma R1 comma R3. So this multiplication will be performed and result will be stored in R1. Okay, and at the end our result in R1, what we want, result in X. We need to perform this store X comma R1. So in that case, from register the value will be stored in memory. So first it will fetch all the data from memory to register, and then whenever there is operation it will use register, so faster. And then at the end the data will be stored from register to memory. There is no in between memory access. Okay, so these are the different instruction formats that we have seen, and in that the number of address fields are different. So that thing we have seen. Thank you.